pleased today to introduce Exponent colleague and a good friend, Bob Caligiuri, to the Wilson Forum. Bob worked at the Lawrence Livermore National Lab and at Stanford Research before he joined Exponent in 1987. Since that point, he's been instrumental in building the firm from a relatively small engineering consulting company known then as Failure Analysis Associates into a more than a 1,000 person comprehensive engineering and medicine and science, comprehensive in the broadest terms in terms of consulting work. Bob is an internationally recognized leader in understanding and mitigating environmentally induced cracking of engineering materials, which you'll hear a lot more about in today's presentation. Bob, it's great to have you with us. I'll turn the floor over to you. Welcome to the Wilson Forum.
Thank you. Can you, let me share my screen here. Can you see it? Can you see the presentation?
I can't see it yet. Are you
Oh, here we go. Just a minute. Let me
Yep.
bring it up here. Can you see it now?
Yep, perfect.
Okay, great, good. Well, thank you, Ron. Like Ron said, I've known him since, actually, I knew him well before he joined us in full time. We had to work a little bit to talk him into joining us, but he did finally. And I'm pleased to hear that people are aware of our company. And I forgot the person who was talking about P9, but if you want some information about P9 and what happens to it at elevated temperatures, I can fill you in on that because we have a big project on that. Anyway, what I want to talk to you today is a project that we did a long time ago, back in 2006 to 2008. Why would I dig back in ancient history? Well, because this is a really good example of how you can use Failure Analysis Associates, which was the name of our company until 1994. I should share with you a story. Roger McCarthy was our CEO back in the 90s, who also was an MIT PhD. And when he took the company public, and he used the stock symbol was FAIL, fail. Yeah. So when we got another CEO, Mike Galkey, he changed it to Expo for good reason. Anyways, but the company was Failure Analysis Associates, and this project is a good example of how failure analysis can be used to do risk mitigation services and applications. That's why I decided to use this one here. It's not litigation. It was a very interesting project that we did. So it has to do with the pipeline system in Peru. So let's see here. I'm going to do this here. Advance. There we go.
Yeah.
So actually, I think I'm not going to spend any time with Exponent, as you folks seem to know a little bit about it. It's a leading engineering and scientific consulting company, solving problems for a lot of clients. It's the key here for this particular project is multidisciplinary, and we've got pretty much every discipline from A to Z covered, from architects to zoologists in the firm. We do more than 4,000 projects. Sorry,
going? Is it started?
Folks, we should mute our microphones if we're there. You go. Thanks, Bruce.
Yeah, thanks. We do about 4,000 projects a year. Interestingly enough, the average project size is about $30,000. Give you an idea about that. But then we do mega $1 million projects too. And our clients are corporations, law firms, associations, and governments, probably in that order. And it's about a mix of 50-50 between what we do, what we call litigation support, which is what I primarily do. And that's what Ron pretty much did when he was with the firm full time. But the other 50% is supporting clients solving their engineering and scientific problems, like with the electronics industries and things like that. So it's about 50-50 mix. Okay. So what are we talking about today? It's the Camisea transportation system. This is a pipeline system that was constructed in the early 2000s to bring gas and gas liquids from Peruvian Amazon to the coast. Oil and gas was discovered in the Amazon back in the 80s by, I think it was Shell, but they couldn't figure out how to get it from the jungle to someplace where it could be used or at least shipped. Finally, in the early 2000s, a project was funded by the Inter-American Development Bank. That's an interesting organization. There's 3 or 4 of those that are basically funded by countries, first world countries, putting money into a bank And then that bank uses that money to build infrastructure projects in third world countries. And there's an Asian development bank and there's an African development bank. This bank is focused on developing infrastructure projects in Central and South America. And it has two 24-inch diameter pipelines, carbon sealed pipelines. It was constructed and operated by a company called Transportation Gas de Peru, TGP, and went into operation in probably 2006. The interesting part here, and what's kept the Amazon oil and gas reserves from being developed, is that there are 3 hazard zones that this pipeline must traverse to get the stuff from the jungle to the coast. So the Amazon hazards like mudslides, floods, and indigenous populations. Why would that be a problem? Because there are people in the Amazon, as you well know, who don't want to be bothered by the Western world. And so they had to be very careful to construct this pipeline system around those villages and areas of indigenous people. So it was a hazard in that sense. Had to cross the 14,000-foot Andes, where you have rock slides and other issues, and then across the coastal plain to the coast. And as you know, it's a very high active earthquake zone. So it was a very much of an engineering challenge to develop this system, which they did. The system goes from the jungles in the Amazon all the way through the jungle, across the Andes, out to the coast, and where it ends and then is processed or shipped out. It's about 1,000 kilometers long, the system, and you can see from the lower picture exactly where it is in Peru. What happened here? Well, not too long after they started this system up, these 2 pipelines, the one carrying the natural gas liquids suffered 6 leaks within a few months of operation across all 3 hazard zones. And one of the leaks burned down an indigenous village, which was not a good thing. People were pretty unhappy about that. So that was problematic. So what happened next? Here's where the leaks were actually. There weren't any in the earthquake zone, but there were 4 in the jungle zone in the Amazon, and there were 2 that were sort of as the pipeline system crossed the Andes. These are incidents 1 through 6. 1, 4, 5, and 6 were in the Amazon. 3 and 2 occurred as the pipelines were crossing over the Andes. And we'll talk a bit more about what these incidents were all about. That's the failure analysis part of the project. We were contacted by the Inter-American Development Bank, who became very concerned about this investment that they made. And so they contacted us to investigate the causes of these leaks and, more importantly, to help TGP develop methodologies to mitigate the risk of future leaks. We were actually worked directly with TGP and paid by TGP, but with the direct support of the IADB behind us. So what did we do? Well, first of all, why us? Well, because we were uniquely positioned to help here because of our multidisciplinary team of qualified specialists with lots of industry experience, professional engineering. We have we got more than this, but applicable to this project were mechanical engineers, metallurgists like myself and Ron, geotechnical engineers, hydrologists, geologists. All of these disciplines were important in trying to resolve the causes of these leaks and help mitigate future leaks. So we were really uniquely positioned, and I would say we were probably the only company that could really do this on a consulting basis. What did we do? Well, the first thing we did was to identify the factors for the first 6 spill incidents. What happened there? Then review potential systemic risk associated from design and construction. Are there risks associated with the entire pipeline related to its initial design or to its construction? Risks that would apply across the entire 3 of the hazard zones. Then we did a risk assessment on 4 areas of risk that we identified, specific areas: geotechnical, pipe integrity, seismic-related risk, and scour-related risk. And you'll see why those are important in a minute. Then we recommended technical risk mitigation actions to the bank and to TGP to mitigate the chances of this occurring going down the road. What did we do? Field inspections of more than 50 sites along the right-of-way in June and September, like I said, a long time ago. That included out in the Amazon, which was quite an interesting experience out there in the Amazon, fighting off the bugs and the snakes. We did 400 documents. This is typical of us, 400 documents we reviewed. We did metallurgical work on the fractured pipes. We did an engineering analysis, and we did some risk assessment work as well. This was over a period of about 2 years this work was done. Let's talk a little bit about what happened. Spill incidents 1 and 5, both of which occurred in the Amazon area. These unstable soil conditions, mudslides, and moving soil was a significant contributor. And basically, as the soil moved, put increased loading on the pipeline, produced subcritical crack propagation in the natural gas pipeline, which ultimately led to the failure that you see in the picture down below. And the pictures on the right show the soil. In the lower picture is what happened, the soil of the landslide that moved, and the picture up above is some of the remediation work that was done. So here, a little closer look, you can see in June what it looked like, the soil that had moved, and then you can see where the rupture was. And this moving soil is bad news on pipelines. And as you'll see, is a sort of a theme here amongst many of these failures. And then afterwards, you could see the work that was being done that should have been done in the first place to prevent the soil from moving. And you could see the crack in the pipeline that resulted from just being pushed by this massive amount of soil and cracked the weld. This 5 is another similar incident here. You can see another landslide slipping, and the work that was, you could see the soil moved in the upper right picture, and again, another broken pipe right there at a weld. Due again just to overload failure from the soil moving on it. This one's different. This is a crossing of a river, and what happened here, there was a pre-existing dent in the pipeline, and the floodwater, which is pretty common in the Amazon, triggered an overload failure. And I have seen this before in other pipeline systems, where the water actually, if there's some problem with the pipeline, the moving water can actually introduce an overload failure in the piping, and that's what happened here. It was under the water, but it failed. This is another one here that in the Amazon, and you can see again, basically another soil movement issue here. And this pipeline you can see in the lower right, it looks like it's bent in the vertical direction, but the picture again it's really in the horizontal direction. So the piece of the pipe on the left-hand side got bent by the soil movement relative to the pipeline on the right, piece of the pipe on the right, and just cracked the pipe through and leaked. These are the two that occurred in the crossing of the Amazon. You can see the topology and the environment changes substantially as you climb up these mountains. And it occurred again in kind of close to the peaks of the Amazon, and you can see a picture of where it leaked. And here's our friend again down below, cracking a weld. This was different. This was time-delayed hydrogen-induced cracking in this pipe. And if you look, the pipe had passed hydrostatic testing it was pretty tough steel. So it actually passed its hydro test. But multiple hydrostatic pressure cycles and operational pressure fluctuations propagated this crack. The red arrows are where the crack was initially due to hydrogen-induced cracking during the welding process. Then that crack just grew with time due to hydrostatic testing and just fluctuations in pressure, which I've seen many times now in pipeline systems. It's interesting here because certainly people with operating pipeline systems, a lot of people think that hydrostatic testing is the be-all, end-all to determine the integrity of a pipeline system. Well, it can help find things that are about to leak, but here's an example of where repeated hydrostatic pressure is not a good thing, because it basically drove a dormant defect in a pipe, caused it to go through wall and lead to a failure. 3 is a different case again, another landslide movement. You can see the slope of the mountain here. And this was a huge rock slide that came down on the pipeline. You can see the right of way there, and just came down and just nailed this pipeline and broke it, as you can see in the bottom right picture, another overload failure. And what they had to do was basically drill a tunnel through that mountain, through that ridge, to mitigate the risk of further rock slides. And again, there you go, another picture of a broken pipe. You begin to get the picture here that there's a theme here. And the theme basically is that there were basically four kinds of risks that were looked at: design-related risk, construction-related risk, geotechnical-related risk, and scour-related risk. Geotechnical turned out to be one of the biggest risks related to this pipeline. As you saw, 4 of the 6 at least were related to just earth movement in one form or another. So we recommended some risk mitigation methods for these risks and develop monitoring methods going forward for TGP. The design-related risks, potential systemic design-related risks impacting future pipeline integrity. That's what we were looking at. Hydraulic risks, meaning risks from dispressurization of the pipe or minimal. In other words, the pipeline had been designed to carry the pressure that they were seeing. And in addition to that, there were designs to mitigate geotechnical measures that were there, but some of them were not implemented correctly, and that's why we had some of the leaks. But the design was in compliance with AFOCL ASME codes. So the design in and of itself of the pipeline system, the pipe metal, the welding processes generally were within code specifications. Construction-related risks. Again, the pipe material was manufactured per API 5L standard. The girth welds were radiographed per API 1104. But as I showed you, one of them had a hydrogen-induced crack in it, so it got through the radiography, and I've seen that happen before in other pipeline systems. It was tested hydrostatically per ASME, but we saw the effect of that on that hydrogen-induced crack. Geotechnical remediation methods were implemented during and after construction. However, the terrain proved to be complex and challenging. And that's what the problem was with this pipeline system. It's primarily related to the difficulties of bringing it from the rainforest to the coast. And that caused the leaks. And those factors were not really consistently thought of as this pipeline system was designed. Risk to geotechnical conditions, like I said, this was just a nightmare of a construction project, trying to design a system and build it to traverse these 3 hazard zones and avoid the indigenous populations that were in there. It was quite a project. And they did think about the geotechnical risks, but they didn't quite implement them completely correctly. As a result, based on our recommendations, the operating company engaged in an extensive geotechnical stabilization program. I'll show you some pictures of that, what they did. And we did a qualitative geotechnical risk assessment, trying to identify the areas at most at risk to this pipeline from a geotechnical perspective, qualitative risk assessment. And they used this new risk assessment to add new monitoring and control measures. For example, devices were inserted along the pipeline to look for potential movement of earth, and sensors were put along the right-of-way through the earthquake zone, and implemented a number of control measures to try to keep this from happening again. So this is this is what a qualitative risk assessment looks like. It's not quantitative, it's qualitative. So basically you have severity and likelihood. Severity is what would happen if something broke, and you rank it 1, if it at a particular location, you rank it 1 through 4. And then what's the chances of it happening? And you rank that 1 through 4. And you can see that as you move from the upper left to the lower right, it becomes the risk increase substantially. So you want to stay out of that lower right coordinate. So if you've got potential risks in the 4, 3, 5 region, those are the ones you need to focus on and try to mitigate those. And that with that methodology and that idea, that's what TGP did with our recommendations as they went along the entire right of way, trying to reduce the risk, primarily from a geotechnical perspective. So what did they do? They basically did weekly inspections of the pipeline at our suggestion. So they walked the pipeline right away and looked for potential problems. Strain gauges were installed, piezometers were installed, slope inclinometers were installed. survey control, rainfall monitoring, all of these things they implemented now, trying to head off a potential landslide, a potential rock slide, mudslide, trying, and if it looks like it's going to happen, come in and try to build the area up to strengthen it. So here's some, you could see the work that had to be done here. These are some of the things that were done. Gabion walls, which are basically piles of rocks, pin piles, overburden, removing the soil from the pipe, digging ditches to take the water away, breaking the surface. You can see that. These are standard techniques. And drainage channels. All of this work was done along the pipeline, which to some degree should have been done in the first place when they built this pipeline. And it was a massive effort to reduce the risk of geotechnical hazards. Here's some more examples of it that you can see the work done. You can see what it looked like in the upper left here, Exponent. We took a picture in September, and the picture's in September, and you can see the work that's been going on here. And then this is the one in the lower right there was particularly challenging as they tried to, you look at that, that's almost a 90-degree slope above the pipeline. And the work that had to be done to minimize the risk of that coming down on the pipeline was enormous. You can see the walls that were built dealing with water channels here in the upper right picture. It was quite the effort. So they did mitigation methods at over 100 sites that were identified by the geotechnical qualitative risk assessment to do the work. Here's some more examples of it. You can see on the upper left is before any work was done. And then you can see afterwards what it looked like. You can see the substantial change that was done to prevent this. This is in the Amazon area, and the work that was done to prevent soil movement. You can see in the upper picture there, the big slope, and the pipeline was going up that slope. And then they went ahead, and this is looking downslope, but you can see the work that was done to try to keep that mountain from sliding down on the pipeline. And the other side, on the right-hand side, is another example. This is crossing over the Andes, and you can see that that arrow is pointing to a problematic area in this whole mountainside. And if you look in the lower right, you can see all of the work that was done to try to minimize the chances of rock slides as this pipeline goes through. That the arrow there, the white arrow, is showing where the pipeline is. Slope stabilization was done here. Here's another example. You can see this is actually, I think I showed this before, but you can get an idea of the slope of this mountain, this pipeline going up this slope or down the slope, whatever you want to look at it. And then what they did in the lower left to minimize the movement of that hill. And again, here's another example in the upper right. You can see the soil you can see it slumping there. The dashed red line is slumping of the soil down onto the pipeline, which is sort of where that red arrow is pointing at. And you can see in the lower right what they did, completely changed the topography of this area, and to minimize the chances of that slump coming down and impacting the pipe. Is what we learned is that soil is just bad news for the pipeline system, and you need to keep it away from the pipe. So what are some of the other risks we looked at? There was, we know that radiography and hydrostatic testing was performed during construction. And there was an inline inspection done, magnetic flux leakage. And basically at that time, there was really no evidence of any sort of external or internal corrosion. So there really wasn't a long-term risk related to corrosion from a pipeline integrity perspective. So felt pretty good about the integrity and the ability of this pipeline to resist corrosion. There were no failures of the pipelines due to earthquakes, but as we all know, that's a real serious risk, and the risks are due to uncertainties in the evaluation of permanent ground displacements. We recommended that there were some seismic studies done, but we felt that they were insufficient, that they felt they needed to do more seismic studies and assess the potential for given earthquake magnitudes of what that might have on soil movement. And TGP actually went through and did that over a period of time. And so we believe now that the risks associated with earthquakes are minimized. You always have to remember that there's no such thing as zero risk. And all you can do is work to mitigate the risk, whether it's a pipeline system or whatever it is. You work to mitigate the risk, minimize it, but to turn it to zero is that's not engineering possible. Scour-related risks, I showed you one of them. That's where that dent occurred in the pipeline, and the scour from the water with moving water can carry a lot of stuff with it. And where that scour occurred that led to the failure, there was a lot of boulders coming down that water that impacted that pipe. And with the dent there, they couldn't take it, and it broke. So potential risk due to uncertainty of the scour hazard. That was really not thought of when they built this pipeline system. And so we recommended some additional comprehensive scour studies, meaning, okay, there were many water crossings as this pipeline traversed from the sources of the natural gas, liquids, and gas through the Amazon. There were many water crossings, and we recommended that they consider what happens. Sure, when you build the pipe, the water is at a certain level, but you got to anticipate what's going to happen during big rainstorms, and that's a big deal there in the Amazon. And they hadn't really thought about that very much, so we recommend that they go through and consider for each of these stream crossings, waterway crossings, what happens if you get a really high flow water through there? What can you do to prevent that from failing? So what were the conclusions here? The pipe material selection, we felt, and during there's not a problem with the construction of the pipe itself, with the actual pipeline itself, which is not always the case. But in this case, we felt that they had done a pretty good job to not really propose a risk. There was very little corrosion damage, and we've asked TGP to continue to investigate any potential risk arising out of these girth welds. We did see one girth weld failure due to hydrogen-induced cracking. The geotechnical risks were mitigated by just doing massive amounts of soil, reconstruction around the pipeline, and they have been reduced now. And they were doing additional scour and seismic studies to address these potential pipeline integrity risks going forward. So it was a very interesting project to connect failure analysis, why did the pipe break, to what do we do to keep it from breaking in the future if we can. And was a very successful effort because there's been no additional failures on that pipeline over the years. So, thank you.
Bob, thank you very, very much. That just a comment. You mentioned risk assessment many times during your presentation. You might be interested that one of our speakers earlier in this program was Ali Mosley, who is I forgot if he's now the director of the Garrick Center at UCLA. This is,
well, of course, Garrick was the developer of quantitative risk assessment for nuclear applications. Yeah, he was we bought his company.
Yes, that's exactly the point I was getting to.
Oh, okay.
There are two interesting offshoots of all of it. First of all, John Garrick, as you point out, was the father of risk assessment. But secondly, and I think now of Dan Metley, who's one of our crew here today, Dan Metley and I served when John Garrick was the chairman of the Nuclear Waste Technical Review Board. We were members of the board at that point. We served on the board and the staff, and John was a wonderful guy. He really was. And it was just an interesting experience. But my major point is that risk assessment is something we've heard from Ali about, and he's a very good spokesman. But let me ask a technical question here. That pipeline looked like it must have been about 400 miles long, I think. It
was just about under 1,000 kilometers. Maybe.
Yeah, holy mackerel.
Yeah.
And it is operating today?
Yes.
Now, I'm just curious, when it was designed, obviously the design, it sounded like they had a design that looked workable, but in some respect, I think you said it may not have been implemented fully.
I think what I meant by that is we think the actual construction of the pipeline was okay. In other words, building the pipeline, getting the steel out there, welding it up, that sort of stuff, and putting the bedding around it and all those sorts of things was done pretty well.
Yeah.
What was not really anticipated was the extent of the what I call the geotechnical hazards.
Mm.
They didn't really, I mean, the right of way was just, I've got other pictures of the right of way, you just can't believe it.
Yeah.
Just what it had to cross.
Yeah.
And I don't think they fully appreciated those hazards. That's what led to at least four of the failures that they had were all related to soil movement, either through mudslides, rock slides, landslides. They didn't really appreciate that. So they didn't prepare the right of way sufficiently to really mitigate those risks.
Hmm.
And as a result, they had problems. So when our recommendations, they went back, took another look at that, and at those 100 or whatever they were, 200 sites, they did some significant reworking of the
Yeah.
local soil and topography conditions. That's what really went wrong here.
Yeah.
You could the hydrogen-induced cracking problem. Yeah, that was kind of a one-off thing.
Yeah.
But the problem with just this pipeline, they can't. You got a pipeline that's 24 inches in diameter. It's probably close to an inch in wall thickness. You think, well, heck, that can put up with anything. No, you got to
Right.
realize the impact of that soil. So that's, I think, was the biggest problem they had.
The remediation must have been costly to implement, though, was it?
Yeah, it
And
was.
did the bank pay
The
for it?
bank,
Yeah.
yes, the bank had to. I mean, the way the bank works is that TGP took a loan from the bank. I mean, the bank just doesn't give you money. It's like any bank, they loan it to you,
Yeah.
and then you pay it back. And
Uh,
so in the short term, the bank paid for all these. That's why the bank brought us in to make sure what was done was needed, but was going to fix the problem.
sure.
And so the bank paid for it, and then TGP had to pay the bank back. I don't know the status of that now, but yes, the bank came in the short term and funded all that work.
Gotcha. We
It
have
came
some
out of
hands
your
up.
tax dollars. Okay.
Of
Don't worry.
course. Let's go to Eddie.
Yes, I spent about 10 years at EMC, plus going back into the telecommunications job that I did in the early 90s in reliability engineering, essentially. And one of the things we used to have is, which we did, particularly with new chips, actually, in integrated circuits, which were very complex, was to look at, and we put into practice basically processes like FMEA, failure modes and effects analysis. And every time we did that, we always plunged into all the things that could go wrong and all the extreme conditions that we would likely face. Plus putting in our numbers, reliability, and so forth. I don't know if that is done in this kind of engineering environment. And because to me, it sounds a bit like that initial preparation was not done. Is it done as standard engineering practice in this regime? My other question on top of that is materials. One of the things that struck me recently is in the oil and gas drilling business, which never has developed really new technologies for drilling until quite recently, when people started thinking about drilling very deep. But it strikes me with the pipeline business, you need more types of material that are flexible and so forth, that can take and withstand perhaps movements of soil and so on. So I'm just sort of throwing those things out at you, and wondered if you could respond to them.
Well,
I much enjoyed your talk, by the way. Very interesting.
yeah, thank you. I they did. I mean, no, what I showed you in terms of the remediation methods, the geotechnical approaches the approaches to mitigating geotechnical risk, those are standard techniques. That's not something we invented by any means. Our geotechnical engineers have experience with that. So it's not like we invented something new there. What happened here is that the risk assessment that you talk about, Eddie, was not really done very well here from that perspective. The risk associated with bursting the pipe, with corrosion, all that stuff was done pretty well. This category of risks, given the challenges that it faced crossing these zones, was not thought out very well. And you probably saw that in some of the pictures that I showed before they did anything. pipes going up the hill like this. And then they went and they, layered it like this. And that was probably not done correctly. There was actually a lot of infighting there between the contractors that built this pipeline. In the end, there was. I can't remember exactly what happened, but it was an Argentinian company that actually built it. And there was some dispute between TGP and that company over what the heck did you do here? And I don't know how that worked out, but the answer is yes, there are definite risk assessment methodologies. You mentioned FMEA, and there's quantitative risk assessment. That's what John Garrick invented for the nuclear industry. None of that was really done in the past as a first pass through building this pipeline.
That's
In
what it
terms
looked
of
like to me.
in terms of materials for pipelines, pretty much any transmission pipelines made out of carbon steel. And they're welded carbons, butt welded carbon steel, seam welded carbon steel, because you've got thousands and thousands. I mean, there is hundreds of thousands of miles of transmission pipeline in this country. Around the world, I have no idea. But you can't be putting exotic materials into that. So what you have to do is to mitigate the risk by making that pipe correctly, welding it correctly, so you minimize those risks, and protect it properly, either through cathodic protection, through putting it in locations that you're not going to get soil movement and things like that. So you deal with the risk associated with it, not so much by coming up with exotic materials, but basically working with the carbon steel and then working around the other risks to minimize it. So that's I think I answered your question. Maybe not.
Well, my point is that all these mitigation efforts are highly costly. So I'm a little, I wouldn't say I'm surprised, but it would be nice if you did at least some research into new materials, perhaps new stills, new types of, and so on, that would lower the costs and need of these kinds of mitigation. So the industry as a whole never seems to me to be wanting to advance and find ways in which they could lower costs through research and development of new materials. Is that a kind of
I think it depends upon, the oil and gas industry covers a lot of things. It covers everything from the transmission piping systems to downhole drilling, and to process, what do you have in a refinery? And I would say there are some attempts to develop new materials. I just think in the world of transmission pipelines, I don't see that happening. I'm not sure you can, but you can certainly, I mean, there's a lot of advanced materials going into improvement in materials in certain, like in the refineries and certainly in downhole drilling. I would say it's way behind what you find in other industries. I would agree with that. But and companies are loath to develop nickel-based alloys for for a refinery, but they look at the applications where they are. So, I mean, I think you're generally right that you don't see a lot of new materials development in that part of in that industry, but there is some that's going on. You see them advanced materials development going into things like aerospace, electronics, for heaven's sakes. Not so much not as much in the petrochemical world.
yeah, I was thinking actually as well of things like additive manufacturing and that kind of stuff for pipes and so on. I don't know if that helps.
Yeah, well, we can talk about additive manufacturing some other time, but
yeah, and I'll leave it at that. I've taken up enough time.
I have my own views on that.
Okay.
All right, let's go to Albert. You're muted, Albert.
Sorry about that.
Yep.
Very impressive project, Bob.
Yep.
Question about what you call the hydrogen-induced crack. What is the source of the hydrogen?
From the welding process. If you don't if you don't, well, I'm sorry, finish your question.
No. Go ahead. In the welding.
Yeah, so when these are the circumferential welds that are done in the field. And if you don't protect the environment properly around that weld, you can get moisture in there. And if you get, I don't know what kind of, I can't remember the electrodes they were using, but hopefully low moisture electrodes. But if you get moisture in there, you trap it in there and you create hydrogen during the welding process, which collects inside the weld. And that can induce cracking inside the weld. And in this case, it was subcritical cracking and even survived the hydro test. But then with the hydro test and probably more likely the pressure fluctuations in the pipeline drove that dormant hydrogen-induced crack through the wall and caused the failure. But the hydrogen source of the hydrogen was the weld. It was moisture and entrapment in the welding during the actual welding process.
And with the hydrogen, was that hydrogen produce any embrittlement that could have contributed?
Yes, that's the cracking. So the hydrogen causes the crack to form inside the weld metal. Or
it's a subcritical crack, but it propagated later, but it was subcritical at the time it was produced. Yes.
The hydrogen embrittled the material that caused a crack that was internal to the weld.
Okay, sounds good. I'm glad the hydrogen doesn't come out of these natural gas liquids.
No. If that was the implication, not at all. It's not
Right.
the fluid going through the pipe did not contribute to that. In fact, the fluid going through the pipe, the natural gas liquids, has really no effect. We saw no effect of that on the internal, nature of the pipe.
Thank goodness for that, because it would have been happening all the time, everywhere.
Yeah, I don't think.
Back to John Garrett and his work on nuclear safety. I always thought of the report from the Rasmussen report on nuclear safety. Was Garrett involved in that?
I don't know.
I don't think Rasmussen was at MIT, of course, but I don't think John Garrett was a part of that study. I don't think he was.
But the Bible, in terms of doing risk analysis for nuclear reactors, was the Rasmussen report, and actually I worked on applying that in the oil and gas business.
Oh, okay. Okay.
Anyways, my last question, actually it's more of a comment. I worked on similar banks like the World Bank and the ADB, Asian Development Bank, on big projects. And oftentimes the host country hopes not to pay back the loan.
Yeah, that's true.
Is that the case in Peru too?
I think they were really counting on that. But in the end, I don't know what happened. But yeah, I can tell you that they were hoping not to have to pay it back. Yeah.
Well, thanks, Bob.
It turned from a loan into a gift.
Yeah. Right.
Yeah.
Well, lucky it's not our tax dollar, though, for some of these banks.
Well, I mean, I think it's a good use. The bank is a bank, and they were technical people in the bank, not particularly highly technical. But I think it's a good thing. I mean, that pipeline system now has been working since 2008, and I don't know what it's done for the revenues in Peru. Peru has got a lot of its own problems, but I think those projects, by and large, are worthwhile.
Sure, thank you.
Let's go on to Walter.
Yeah. Hi, Bob. Great presentation. I'd like to carry on the discussion about the hydrogen-induced cracking.
Mm-hmm.
And then bring that to today, where there's a lot of proposals about using hydrogen as a fuel and mixing hydrogen in with natural gas in today's pipelines. What's your opinion about using pipelines to transmit hydrogen throughout the U.S., whether it's part of a mixture with natural gas or just pure hydrogen?
I would say that it's not and I let Ron weigh in on this too, but I don't see that being a huge problem because these carbon steels and I'm assuming you're talking about transmission piping, not necessarily process piping. Yeah.
Right.
These steels are not really susceptible to hydrogen embrittlement. Where it becomes a problem is when you get water in there and stuff like that. Then you can get some cracking problems there. But in terms of just transmitting hydrogen in the gas state, I'm not sure that's such a big problem. At least I haven't seen it. So go ahead.
What about the fact that the hydrogen molecule is so small that it can find leaks where the natural gas couldn't get through, the hydrogen could?
Oh, you mean a leak from in other words, you've got a leak in your pipe that's so small that the natural gas liquids don't get through, but the hydrogen could. Yeah, that's a possibility for sure.
But let me just add a point here, though. You know, it isn't that we cannot transport or store hydrogen. In fact, we do it all the time in laboratory cylinders, and they're essentially low strength carbon steels. And the pipelines are pretty much the same material. So the pipeline itself, I think, that transports gas today, or could just as well transport molecular hydrogen in the future.
Yeah.
You know, it needs to be demonstrated, but I think it's certainly possible. So that's just, I think we're on the same page with that.
Very good. Thank you.
Yep. Walter, no, Michael. Sorry, Michael. Go ahead.
Yeah, a technical question, Robert. I was the one that mentioned P9 earlier. We're running a vacuum tube, 12-inch diameter, P9, 3/8 inch walls, 28 feet long with a 20-foot heated zone, and we're introducing biomass into a vacuum that ranges from 5 to 25 inches. And the vacuum changes from it pulsates as we put in the biomass, and the gases and the cellulose begin to vaporize. Of course, the vacuum goes down, so it's kind of pulsing a vacuum. We operate at max 1,000 degrees. I'd like to go to 1,400 at times. How am I doing so far?
I will tell you that P9 is going to be a great material for your application. And it's not outrageously expensive, but it's pretty good for what you're talking about. Where you begin to get a problem is when you heat it up too much, and it has a drop off in strength levels as you get closer. I'd be worried about using it at 1,400. I've seen P9 turn into a piece of spaghetti in a furnace application in a petrochemical plant, because it got overheated. And it got overheated because the pipe got plugged up with coke. So it overheated, and it was meant to operate around 1,000 Fahrenheit. It got up to 1,400, and it just bent like a piece of spaghetti. So I think as long as you control the temperature to where you are and minimize the risk of overheating, you'll be fine.
Great. Thank you very much. Appreciate that a lot. That's great. Wonderful. Just another quick question. In these types of projects, you get distance, and whether it's mental, local, did you have any issues?
Michael, oh, there we go. Okay, we couldn't hear you.
What's
either.
going on?
Try to get-
Sabotage? How much of an issue is that when you're talking about 1-inch thick walls and carbon steel?
I would say you need to be very concerned about that. And that's why they would patrol the pipeline. And there are people who think they can drill a hole in the pipeline and steal stuff. Happens all the time in Africa.
Oh, yeah.
And that's why you have these big fires sometimes in Africa. And there was cases back in the Trans-Alaska pipeline that they found occasions where people would shoot holes through it. There are people who think it's fun to shoot a hole in a pipeline until the gas comes out and burns them. So yeah, I'd say it's a big problem, and they actually that was a hazard they did consider, and that's why they were very carefully monitoring the right of way for that particular problem, and particularly in the Amazon, where you have the indigenous people who may not quite understand what's going on and not realize the hazards associated with it. So yeah, absolutely, these pipelines are buried, so it's not as much of a problem, but there are areas where it gets exposed, and then where it's exposed, you could have a certainly a problem with getting damage from people. The most common damage to a pipeline system, third party. That's the most common failure mechanism in a transmission pipeline. Somebody hitting it with a backhoe, somebody, a big rock falling on it, stuff like that. Is somebody digging around it. That's the number one failure mechanism in a transmission pipeline system, far greater than corrosion or cracking or things like that.
Interesting. Well, they're now talking about CO2 pipelines. They want to pump CO2 across the United States for these bioenergy capture systems. And I would assume that that's probably less of a problem when you're dealing with hydrocarbons.
Yeah, I'm not sure what the risk is associated with CO2 piping that. I don't really think there is any, much less of a risk than flammable hydrocarbons for sure.
I guess. Thank you so much.
Albert, you're muted again, kid.
Back to the issue of embrittlement, there are joints that has O-rings made of polymeric or petroleum product. Would hydrogen affect the integrity of these joints? Or
Okay, if we're talking about transmission of hydrogen around the country through transmission pipelines, you don't really, I mean, you have valves and things that have gaskets in it, but the actual pipe itself won't have any gaskets in it. It's all welded. But I think, and I defer again to Ron, but I would think that hydrogen could degrade some of those gaskets you have in valves and things like that. So
I think it absolutely could. That's the kind of issue that has to be dealt with and demonstrated to be manageable. But that's an issue.
yeah. So trying to replace natural gas with hydrogen or a mixture in the house, in your burner or the furnace, you have these gaskets.
Yes.
Yeah, that's true. I don't know if we'll ever have hydrogen powered
Furnaces.
gas tubes, I mean, hydrogen powered cooktops. I don't know about that, but
You know what,
sure.
Albert, one of my favorite projects was to work with a group of people who were interested in hypersonic vehicles. And the fuel for hypersonic vehicles is thought, the best fuel is thought to be hydrogen. But you have to think about how you're gonna carry it in this vehicle. And that's not trivial. We spent a lot of time thinking about that. I think we came up with a good solution, but I don't think I could talk about it. I think it's classified, so I won't say anything more.
But
Well, there are
was it liquid or
hydrogen-powered vehicles.
compressed?
What's that? What's
Was it
that?
liquid or compressed gas?
Yeah, well, I'm not going to say anything more.
I mean, there are hydrogen vehicles with using a high compressed gas. Yeah,
Yeah.
I don't think they're very popular, but I know they did try to do that. So
Yeah. Let's move on once again to Eddie. Go ahead.
Yeah, actually, you just made me think about NASA's rotating detonation engine. But I won't say anything more. But my curiosity is with these long pipelines, whenever you get a leak or a break, how do you how do you switch off that segment? You mentioned there are valves and so on, and I was wondering just, what are all the safety valves, if you will, from either overpressure, for example, when it goes up a mountain? Is it possible you get a back pressure that could do things, and do you kind of alleviate that through a valve system, or you don't care? Because going up a mountain a few thousand meters ain't no trivial height.
Yeah, these pipeline systems have compressor stations are all along the way to because as the stuff moves to the pipelines due to friction, it loses some of its pressure. Right. So they have pressure, compressor stations or pumping stations if it's a liquid. So they're periodically along the pipeline, and they don't need to control overpressure. They need to keep the pressure up in the pipeline to keep the stuff moving. There are shutoff valves in these pipelines, and spaced various distances apart. One of the problems that came out in the big San Bruno pipeline failure was a gas line for PG&E, was that they didn't have automatic shutoff valves on it or remotely controlled valves. So they had this big gas leak that's burning houses down. PG&E was frantically looking for the shutoff valves. So they had to send guys out in trucks to try to find them and shut it off. Oh my God. Basically, the newer pipelines that are being built these days, for example, the Dakota Access Pipeline, they have basically either automatic shutdown valves if the pressure changes, or they have remotely controlled. So that if there's an issue, the pressure drops in the pipeline, these valves shut off a particular segment. And they are now doing that in newer pipelines. It's not the case in older pipelines, but how long are the segments that are shut off? I think that really varies from the pipeline. But yes, they have a way to do it, and they're automating that now.
Yeah, I know that when I was sort of involved with Hydro-Quebec, with their huge long stretch of cable running from James Bay down to Montreal. It's a couple of 1,000 kilometers. And in various places they needed instrumentation which was independent of the grid itself. So battery powered monitors essentially to check on what was actually happening locally, plus a whole bunch of different transmission methods, fiber optic and wireless, just to simply monitor that. And I when you look at these long stretches of pipeline, is that the kind of monitoring that is done?
There are leak sensors along pipelines, yes, but mostly the monitoring systems is monitoring the pressure in the pipeline and the flow rate.
But you must power it somehow.
I don't know how they do that. How these monitoring stations and these valves are powered. I don't know that. I assume they're battery powered, but
that was one of the big problems that Hydro-Quebec faced, plus the fact that they had to keep the electronics warm in winter and cool in summer. So the air conditioning took a lot of power. And,
well, these pipeline systems have cathodic protection systems, so there's periodically, power stations along the pipeline to power the cathodic protection system. So maybe they tap into that to power the monitoring stations.
I think in some of the newer ones, you actually see solar panels along with monitors along the length of the pipeline. So let's go on to John. You have to unmute, John. Okay, there you go.
Yeah. So, I'm just a couple of terms that you've used that I have. I'm not an engineer, so I don't know what the word, but I thought maybe you could educate me. One just used was cathodic protection or something like that system.
Yep. Yeah.
What does that amount to, or what is it?
Basically, it's putting. There's a couple of ways to do it. There's the passive system where you basically attach a sacrificial anode to whatever you're trying to protect, and so instead of the pipeline corroding or the structure corroding, the anode corrodes. The other way is impressed current, where you actually put an electric current into the pipeline. And by disrupting, and Ron could tell you more about this, but by disrupting the electrochemical process that drives corrosion through putting a current through it, you can minimize the effect of corrosion. The primary corrosion protection system on a pipeline is the coating. These are all coated with various types of coating. Going way back, it would be tar, asbestos tar, and now they're more advanced polyurethane coatings that they put on there. That's the primary barrier to corrosion. But as a secondary, because no coating is perfect, they do an impressed current. So they just basically put current into the pipeline. And if there's a hole in the pipeline, in the coating, it can then protect that hole in the coating by disrupting the electrochemical process. So it's basically putting juice into the pipeline, very simply speaking.
Yeah.
So,
go ahead, John. Go ahead.
No, Ron, you know what you're talking about. Go ahead.
Well, this conversation reminds me of one of my favorite consulting stories, and it provokes a question to Bob. But let me tell you the story first. Several years ago, I was involved in inspecting a water distribution pipeline in Boulder, Colorado. And the pipeline ran from the mountains in Boulder down to a water treatment facility 17 miles away. And they had detected, with sensors, they had some leaks in this pipeline. It was relatively new. It had been installed only maybe 4 or 5 years before the leaks were detected. But they needed to have it inspected, and they needed to understand what was going on. So I was hired. I went out to Boulder, The only way you could inspect it, given the way it was down a mountain, so it was incredible terrain. The only way you could inspect the welds was from the inside of the pipe. This pipe was 24 inches in diameter. So we, first of all, we asked about closing valves to make sure the pipeline's secure. Well, they closed off the valves before I got in this pipeline. I was sure of that. But I had to climb in through a manhole into this 24-inch diameter pipeline on something like a skid you use to slide under your car to change the oil, attached to a rope, and with a guide from the company leading me down 17 miles of pipe. Actually, I didn't make the whole 17-mile excursion, just 6 miles. But along the way, we'd stop at welds and I would be able to inspect them visually from the inside. And I'll tell you, I mentioned this to Bob, and I said that was one of those moments where I asked myself, "What am I doing here?" I mean, there are times when you get in situations as a consultant where you maybe hadn't expected. And unfortunately, I was not claustrophobic, which I couldn't have done if I had been, because 24-inch diameter pipe, and you're lying on your back. It's not very big, but it provokes a question. And the question to Bob is, Bob, when you make these site inspections, you're often in situations where, you mentioned in Peru that there were bugs that you had to deal with, but there are often personal safety issues that come up.
Yes.
There are often even more difficult technical issues that come up, like inspecting the weld from the inside. For how do you do that? And feel confident. And then thirdly, there are the kind of administrative issues that come up with when you get to the point of understanding what the problems are. How do you remediate it, and who pays for it?
Okay.
I'm just curious. What in your experience, what was the biggest challenge you had along those lines? Was Camisea that, or is there another case that was even more of a personal hazard or technical difficulty, or what was your thought? What is your reaction?
Yeah, I mean, the Amazon was an environmental problem.
Yeah.
Just
Yeah.
the Amazon, you can imagine.
Yeah.
But we weren't out there all by ourselves. I mean, we had obviously people from the company there, and they had places all along the line. So the risks there were not huge from that perspective. Personal safety. We in our company we have the policy: if somebody goes and does an inspection, if they don't feel safe, they don't do it. Okay.
Yeah.
Even
Yeah.
if their client is insisting they do it, the answer is no. I'm not climbing up that ladder because I'm afraid I'm going to fall off.
Sure.
In my experience, the biggest one I had was not in a pipeline, but it was in a black liquor recovery boiler in Canada, which these things are like enormous things. And they are burning the black liquor in the bottom that had been left over from the paper making process,
Yeah.
creating steam. And they're running the steam, burning it and creating steam in the boiler. And then of course the residual heat goes up into the penthouse, and they got a recovery system up there. And they've got these pendant superheater panels hanging down. And what was the problem was these pendant superheaters are welded piping, and they would weld them with a tack weld between them.
Yeah.
And they were cracking and leaking. So 3 of us from Exponent, we went into this recovery boiler that was being maintained, and we went all the way up to I forgot, 10 stories up, and we're inside this penthouse on scaffolding, inspecting these welds.
Yeah.
And somehow somebody decided to turn the boiler on.
Ooh.
Oh, geez. Oh, no.
Well, not heat it up, but to pressure test it. Some reason, so we're in there, 3 or 4 of us are in there inspecting these welds. All of a sudden, all these welds started to squirt water out.
Oh, my God.
It's like, holy crap. Well, it helped us because we could find the cracks.
Yeah.
But whoa, I saw that, and we had to get out of there fast. And because I did not know what they were doing. I thought maybe they're going to turn the whole thing on. And so we climbed out. I had to be the last one out since I was the most senior person there. And one of the technicians I had with me, his name is Greg, pretty big guy. And we had to go through like a porthole or a manhole thing. And he kind of got stuck in it because we're all panicky trying to get out of there.
Oh, my
So
God.
I'm here with this boiler going off, the water squirting out all over the place, and he's kind of stuck in the manhole. So I actually had to push him from behind to push him out and push him out. And then I climbed out. So that would say that's the scariest sort of safety thing I've had on an inspection. So nothing to do with pipelines.
Yeah.
Although there was one time I was inspecting a pipeline in South Texas, and it was, the gumbo or whatever they call that stuff in Texas that's hard as a rock. And then when it gets wet, it's like glue.
Yeah.
And so I was down inside this pipeline with boots on and everything. And of course, there's mosquitoes everywhere. But I stood there too long, and I couldn't pull my boot out of the muck. I was stuck. I pulled my foot out of the boot, but I couldn't get the boot out. So finally had to get somebody to come over because I was stuck. Somebody came over and then basically pulled the boot out for me so I could get out of this muck in this trench. So that was kind of scary too, but not as bad as the superheater.
You had to write a science fiction novel about being a consultant. Albert, you have your hand up again. Go ahead.
Question on that risk matrix you presented to us. And
Yep.
you said it was qualitative.
Correct.
Now, given the cost of all the repairs and the cost of any problem in the future, did they ask you to do any quantitative?
No. No, I'm trying to remember now, and I'm not sure why we just did a qualitative approach. Maybe the quantitative one was just too difficult to do. So I don't remember why.
Okay, and then the other question is, had you done it, would you believe your quantitative assessments?
Would I have believed it? Let me just put it this way. The qualitative one was good enough to find the areas of risk. I'm not sure I would have felt. I I know quantitative risk assessment. I'm not a specialist in it. I've certainly seen it done. I'm not so convinced that you can really hang your hat on the numbers that are calculated. I think you really need to use your engineering judgment as part of it. So you can calculate a risk of 10 to the minus something or other, but you got to put your engineering judgment hat on as well. And so just buying the numbers is not something I think is probably good engineering practice, but people do that all the time. And I know that methodology certainly was developed in the nuclear industry, and it's now spilled over into other industries. But I'm not sure I would have just relied on that.
We have a few more minutes and two hands up, so let's take them. John?
So the other thing, a term that I, went over my head was something about magnetic flux leakage or something like that, or what?
Yes. That is a tool. It's actually, the nickname are called pigs, but they're not pigs. They're tools that are very expensive tools, and you run them through your pipelines. And what it can do is there are a couple of different versions of it. The magnetic flux leakage tool is looking for metal loss. And so what it does is it runs through the pipeline. So it's inside, it's an inside system, and it's putting a magnetic flux into the pipe. And if the wall is compromised, it changes the flux fields, and that is then recorded as a location that the flux is lower here, or leaking out actually is what it is. And then so the operator of the tool runs it through, then it takes all that sensor data through proprietary algorithms and determines what the potential wall loss is, any location where they have leakage of the flux. But the magnetic flux leakage means loss of magnetic flux due to a thinner wall, which is corrosion. Another type of tool is ultrasonic. Ultrasonic, instead of putting a magnetic flux in the pipe, it's actually sensing the wall of the pipe with an ultrasonic signal, just like you do from the outside with the tool. And that tool is primarily meant to find cracks in the pipeline. But MFL is magnetic flux leakage tool.
Bob, I personally don't know much about magnetic flux leakage, but what is the resolution, spatial resolution with that technique?
It depends. Usually it's depends upon, there is the probability of detection and the probability of sizing.
Yeah.
And those probabilities are specified by the tool. And that's usually plus or minus 10% on the depth measurement.
But it's sufficiently sensitive to be able to detect corrosion, metal loss due to corrosion?
Yes.
Oh,
Typically,
that's
typically the threshold is it's not going to find things that are less than 10% of the wall thickness.
yeah,
So if you got a corrosion spot that's corroded the wall maybe 5%,
yeah,
that tool is probably not going to pick it up, or you can't really count on it. It's these tool manufacturers run thousands of experiments through controlled pipelines, and that's how they come up with
yeah,
this.
yeah.
So 10% is the threshold, detection threshold.
I get it. I get it. Good. Eddie, you're going to have the last word. I promised Bob we'd finish by noon. Well, it's not noon in California, but I promised we'd finish by noon. Go ahead, Eddie.
Yeah, I'll be quick. I'm just curious because I would have thought by now with pipelines you'd have little robots to be able to crawl on the inside and do a lot of
That's
work.
exactly what that MFL tool is. It's not a robot, but it's controlled. It's a remote controlled device. So yeah, exactly.
I know in the fusion industry, Joint European Tourists had a little robot running on the inside, actually doing repairs, installations, and so on because it's all radioactive. So
yeah, these tools are remotely run, and they're usually pushed along by the fluid that's in the pipe, and they run at a certain speed, so you can inspect miles of pipeline very quickly. The key and the trick is the algorithms that are developed that take all that sensor data and make sense out of it. And it's like reading the tea leaves.
That's why I was thinking about artificial intelligence, whether that would help.
Yeah, I haven't quite got there yet. So
that's all right.
Okay. Thanks, Eddie. Bob, I want to thank you on behalf of all of us for not only an informative presentation, but for a great conversation following it. Much appreciated.
Thank you.
I know it's early in California, but I thank you for getting up out of bed today a little bit earlier than usual and spending your morning with us. Thank you very much, Bob.
Thank you. Appreciate it. Thanks. Take care,
Thanks,
everybody.
Bob.
Okay.
Really nice.